Hello everyone, welcome back to my organic mechanism talk. Just as usual, I want to remind you that arrow pushing always shows the movement of electrons in the reactions. And today we will talk about epoxides, and we'll talk about the synthesis of the epoxides and the reactions of epoxide. First, we'll talk about the first way to make epoxide. The alkene react with peroxyacid. A common peroxyacid is MCPBA. The general structure of the peroxyacid actually shown here. So you can see there's one more oxygen than carboxylic acid, and this oxygen bond is weak bond, but this peroxyacid is a strong oxidant. And now let's look at the arrow pushing mechanism of this reaction. And this actually is a concerted reaction, just one step, and the product will be formed. But in this one step, they will have 4 arrows here. So this shows the alkene, the propene, and this is the structure of MCPBA as a meta-chloro per benzoic acid. So that is the MCPBA. And the first step is the pi electrons from this propene will attack this oxygen. Then break the oxygen-oxygen single bond. This is a weak bond. And this push back to here form a double bond. And break that pi bond of this carbonyl, and then electrons will depronate the proton. At the same time, the electrons between the hydrogen and oxygen will attack this vinylic carbon. So this will just form this product in one step, and then this is the byproduct, meta-chloro-benzoic acid. This reaction is also called epoxidation. Use peroxyacids, and most of the time they use MCPBA. This is the first way. Then make an epoxide is the 2-step consequence. And first step, the halogens in water will convert the alkene to halohydrin. And in this example, I use the bromine water, and the intermediate is a bromohydrin. Second step, just use the base. Here is the sodium hydride. Depronate the proton of this alcohol, and then a intramolecular SN2 reaction will form this epoxide. Let's look at the detailed steps. First, the alkene react with the bromine water, and the bromine molecule shown here, the pi electrons from this double bond will attack this bromine, and then kick off the other bromine. The other bromine will be leaving group. At the same time, the lone pair on this bromine will attack this vinylic carbon to form a cyclic intermediate. It's called a bromonium. It's positively charged. And water now acts as a nucleophile, will attack this carbon, open this ring, and this is intermediate. It's a protonated intermediate. You need a base to depronate this proton, and then to conform the neutral intermediate, which is a bromohydrin. This is intermediate of the first reaction. Second reaction, the base, the hydride in the sodium hydride will depronate this proton of this hydroxyl group, and then make this oxide as the intermediate. This oxide will do a intramolecular SN2 reaction to kick off this leaving group, but it needs a back attack. So this bond will rotate the leaving group here to this way. Then this oxide can attack from backside. So that is the SN2 type reaction. And then it will form this epoxide. Okay, here is the requirement for SN2 reaction. It's a backside attack. Okay, so this is the second way to make epoxide. Now let's talk about the reactions of epoxide. So a common reaction is called the ring opening of epoxide. Nucleophile can attack one of the carbon of the epoxide and open the ring to form alcohols. And under different condition, the product will be different. First, we'll show this acidic condition. Under acidic condition, the nucleophile usually attack this carbon with more substitution here. And then the product will be shown here. This is example, and the product is a primary alcohol here. Mechanism. First step, when you have acid, the first step it will be protonation. The lone pair of oxygen attack this proton, and the protonation form this a positively charged intermediate. And actually, this will be a better leaving group now. And then the nucleophile, the methanol here in this example, will attack this carbon. Open this ring, and then from this intermediate, you can see this is a protonated and intermediate. We will need to use a base to deprotonate the proton, and then product is formed as a neutral. It's alcohol here, and this part is ether. It's a methoxy group here. Now go back to this step. Why this nucleophile attack this carbon with more substitution, not the other carbon, is because if you draw the resonance structure of this intermediate, you can have two resonance. And you can see this is the secondary carbocation, and this is the primary carbocation. To form this in resonance, you just move this electron to oxygen. From this resonance, you just break this bond, move the electron to the oxygen, and this will be carbocation. So since this is a secondary, more stable carbocation than this primary carbocation, so this carbon will be more electrophilic because it will have more contribution to the hybrid of the resonance. So this carbon actually is more electrophilic because it will have a more positive charge, and the nucleophile will attack this carbon, and then the product will be this primary alcohol. Now if it's a base reaction, the product will be different. I'll use the same epoxide. Now this is the basic condition. In the methanol, we have a sodium methoxide. This is the basic, and you can see the product is actually a secondary alcohol here. Now what's the mechanism? When you have this epoxide and this methoxide, the nucleophile actually will attack this carbon. You can see these two carbons are different. This carbon is more steric hindered. This carbon is more exposed. That's why this base will attack this more exposed carbon here. And then break this carbon-oxygen bond, basically open the ring of the epoxide. You may notice that in this basic condition, we do not have the protons here for the protonation for the oxygen. That's why the nucleophile just directly attack this carbon. And then intermediate is actually an oxide. The oxide will be protonated by this alcohol, which is actually the solvent, and just attack this proton. So, and then break this hydrogen oxygen bond, electron go back to here, and then the product will be formed. So just one more step, protonation, and this is actually a secondary alcohol. So it's different with the acidic condition. Okay, so now this is all, not all, but the common reactions of the epoxides. If you have any questions, please let me know, and good luck.